And with this, I will come to introduce myself. I'm Constantin Sanders. I'm senior data scientist at RT since about a year, and I'm focusing on NLP, on reinforcement learning, and we'll have later a part about reinforcement learning from human feedback. Also, I want to introduce Alexander Zapp, who is a principal data scientist here at RT, but he is only in the background and will answer to questions of you in the chat. So if you want to get an answer directly, you can reach out to Alex, who will answer it in the chat directly. We will also have a question answering session at the end. And then we will discuss all your things that came in until then. And with this, I'll head over to Philipp.
All right, thank you. So also welcome from my side. My name is Philipp. I'm a principal data scientist at RT since about 6 months. Before that, I was working as a computational neuroscientist where I explored different machine learning techniques to understand how the brain works, and reinforcement learning was very important in that effort. And I basically carried over my interest in reinforcement learning to the new job, focusing on reinforcement learning in business use cases. Right, then I give over to Brijesh.
Yep. Hello, everyone, and thank you for joining the webinar today. I am Brijesh, and I've been working at Alexander Thumb since about a year now. And I worked in past for developing reinforcement learning systems for autonomous vehicles and robotics. And I guess let's start with the webinar for today. So we have 3 main topics for today. The first one is basics of reinforcement learning and the terminology we used for describing reinforcement learning problems. The next one is business use cases that Philipp will introduce and talk about. And the last one is reinforcement learning from human feedback, which Constantin will talk about. So let's start with basics. And it is my intention here is to just provide a simple intuition of what is reinforcement learning and how we think in terms of reinforcement learning. So before we begin, let's understand what are the learning processes that we as humans use to learn and master a new skill. So for example, let's say we want to learn how to drive a car. So the first option would be we go or enroll into a driving school, and we would then, under the supervision of a driving instructor, learn when to accelerate a car or brake a car or how to behave in general in various driving situations. So the next thing would be, let's say we have our driving license now and we drive to different cities or different locations. And here we use our learnings to, let's say, find similarities in different driving situations, like driving in a city or driving on an autobahn, or let's say how to behave in various emergency situations. And the third option would be we practice to learn or drive a car on a simulator. So this is a process where we would simply drive a car, try to accelerate, brake, follow different traffic rules, and the simulator will in turn give us some feedback so as based on how we drive the car. So these are 3 processes for humans, but what about machines or different algorithms? Well, they are pretty much the same. So this brings me to 3 fundamental types of machine learning. The first one is supervised learning. Here we have a lot of data with the corresponding labels or categories, and the algorithm tries to learn this mapping structure that exists between the input data and the labels, and it will then use this to apply the similar mapping structure or mapping methodology for different unseen data. The next method is supervised learning. Here we have a lot of unorganized data, and the algorithm learns to group or cluster the data based on some similarity criteria or some underlying commonalities between different data points. And this brings me to the third and the final type, which is the main topic for today, reinforcement learning. So it is basically an iterative learning process where we have interacting with a simulator, and it involves making a lot of sequential decisions, as in what we do after every 1 or 2 time steps. So before we dive deep into reinforcement learning, let's have a look at a small demo. So here what you see is researchers have used reinforcement learning to train a hen to pick a particular color. So what happens is a hen does not know how we call different colors. But what it does know is that whenever it tries to select pink colored circle, it does get some food. So researchers are using food as a reward mechanism to train a hen to perform a particular task. Well, and you can see it is pretty good at it, right? And this is exactly the same technique that various reality show performers use when they are performing with a singing parrot or dancing puppies. So now let's dive deep into what is reinforcement learning, how we formulate a problem as a reinforcement learning problem. So what you see here is a general setup of a reinforcement learning process. We have two interacting entities, environment and an agent. On the right, we have the environment where all the interactions take place. It can be like a physical world or a simulator. Sometimes we call a simulator as a digital twin because it replicates a lot of the characteristics of the real world. And on the left side, we have an agent. It can be a robot or a software program or a simple algorithm. But the important thing here is that the agent has the ability to interact with the environment, observe what is the state of the environment, and take an action to interact with the environment. So let us understand the different parts of this loop using our driving example. So here is a simple example where we want to develop an autonomous emergency braking system. So to understand how an agent will react, we have to think from our perspective how we see the environment or the situation in front of us and how we would react in a different situation. So for example, here the agent's goal is to stop the car in a safe manner so as not to injure either the pedestrian or the occupants of the car. So basically, it is responsible for deciding when it has to brake the car and how hard it has to apply the brakes to stop a car. So how this loop actually works is we first provide the state of the environment to the agent. So for this, we extract the data from various different sensors to provide information like the velocity of the vehicle or the acceleration of the vehicle, what is the distance to the pedestrian, in which direction the pedestrian is trying to move, right? And based on this action, based on this state and this information, the agent tries to take an action. So it can decide when it should brake, or should it probably accelerate the vehicle or maintain its velocity. So as soon as it executes an action, there will be some change in the environment. And based on whether this change is positive or negative, the agent will get a reward from the environment. So what you see on the screen right now is one experience loop for an agent. An agent will collect thousands and millions of such experiences in order to learn what is the best way to behave in a particular situation and what type of action it should take in different situations. Now, to help the agent learn and classify which are like good experiences and the bad experiences, we have something called as value function. So what the value function does is it quantifies the effect of each action into a value. So higher this value is, better is this action, or more is the desirability of this action in a given state. Therefore, these values are called as Q values or quality values, which help the agent realize whether an action is desirable or should be executed or not. So based on these Q values, the agent will try to form a policy, which is essentially a guiding strategy that governs the behavior of agent in different situations. So let's have a look at a couple of demos between how trained and untrained agents look like, and then we follow into the business applications. So here for this demo, we have used some environments from the Unity environments to train a couple of reinforcement learning agents. So what you see here is we have a couple of wobbleheads, and their task is to balance the ball on their head. As you can see, they are hardly able to do it, and the ball falls out within a couple of seconds. But after just 10 minutes of training, you can see they are pretty good at balancing the ball. They are making smaller adjustments. The ball is relatively stable, and it is hardly moving. So now the most fascinating thing here is that the only intervention from our side is to provide agent with a correct reward function or provide correct rewards. And the agent learns how to maximize the reward and in turn, how to balance the ball on their head. Here we have another example where you can see the humanoid is not even able to stand properly, and its task is to collect the green blocks. But after a few minutes of training, you can see that it is able to stand correctly, it is able to walk, and it is also able to perceive the environment and collect the green blocks. Here as well, the only intervention from our side is to provide it a good reward structure. So let's understand what are the characteristics of reinforcement learning problems or reinforcement learning agents. So the central idea in a reinforcement learning problem is that we are looking at processes where we continuously have to interact with the environment, we have to collect a lot of experience, and act in a manner to achieve a particular goal. So our first characteristic is sequential decision-making processes. So these are those processes where we have to take multiple steps or multiple actions, one after the other, that are intended to achieve a particular goal or reach towards a particular task. So this brings me to the next characteristics, that is uncertainty and exploration. So what happens is initially the agent does not know what is the environment, what are the dynamics of the environment, and how it should behave in different situations. So it will spend a lot of the time initially to explore the environment and study the outcome of different actions. So this will help it gain some valuable experience about the environment and how to behave. So this brings me to the third point of trial and error method. So in the initial part, it has to try different actions. They can be good actions, they can be bad actions, but it has to try those actions in order to identify what is the feedback and what is the outcome of those actions. And this brings me to the next point of goal orientation. So all the reinforcement learning agents, they take different actions. They also, in order to reach a particular goal or to achieve a particular objective. And to do this, they are mathematically, they are encoded to maximize the total reward. And this reward function contains the hidden objective, or the goal is embedded into the reward function. And the last point is delayed feedback. This means that initially when I showed the reinforcement learning loop, it was that after every action, the agent gets a reward. But it is not always that necessary that it should get a reward after every action. For example, here, let's say the bipedal robot gets additional 10 points every time it crosses 5 obstacles. But to get that additional 10 points, it first has to cross those 5 obstacles. And only then it can discover that, okay, I did get an additional reward. This is what we mean by delayed feedback. So now I'll hand over the presentation to Philipp, who will talk about the applications of reinforcement learning and different business use cases. Philipp? Thank you.
All right, excellent. Thank you very much, Brijesh, for that wonderful introduction to the RL basics and terminology. And in the next part, we would like to focus on how we can use reinforcement learning in the business domain and in solving a huge variety of different business use cases. And what we would like to do here is we would like to give you 2 examples or success stories of reinforcement learning. The first one is about using reinforcement learning in traffic lights control. And the second is about reinforcement learning in energy management. And then we would like to finish that part by giving you a slightly higher level view on the huge variety of business use cases that we can address with reinforcement learning, importantly by always following the same algorithmic structure, but adjusting it and applying it to solve many different use cases that you might find useful or interesting. So we're going to start with the first example, which is using reinforcement learning in traffic lights control. This example is meant to give you just a general high-level overview of the usefulness of reinforcement learning in replacing conventional solutions. And next, we will then talk a little bit more in detail about the actual steps that you need to take to implement your reinforcement learning. Okay, so what's the problem that we are trying to solve? So we are trying to optimize traffic light systems with reinforcement learning. And the particular problem that we are facing with current solutions or conventional approaches is that they tend to be very inflexible and based on highly subjective best guesses. So conventional traffic light systems generally rely on predefined rules in terms of the timing or in terms of how they are linked to other traffic lights and in terms of when they should go green or red or yellow or whatever. And optionally, they can also have human interventions by making explicit but also subjective decisions about adjusting the traffic light systems as much as possible. These conventional solutions have some problems. So for example, these are hard-coded control systems. So that means there can be no learning based on experience. So there can be no automatic or dynamic adjustments to things that worked or that did not work. There can be a manual intervention, but that again is quite effortful and is not automatic or dynamic. These solutions also are based on fixed timetables, which means there isn't really much flexibility in terms of what is the current traffic volume. So there might be different traffic volume on different days, different holidays, or different seasons, and it gets very complicated to try to hard code all of that. And finally, these traffic light systems also tend to be based on subjective experiences, which means that different operators or different designers of these traffic light systems might have different experiences and therefore design these systems in different ways. And the key point here is that reinforcement learning can really help with improving these traffic light systems by introducing the idea of learning from experience. So the basic idea is that we take our conventional traffic light system, but we add something. And what we add is our reinforcement learning agent, which you see in orange here. And the basic idea is that we take our live traffic data and we feed it into our reinforcement learning agent. We train our reinforcement learning agent and then ideally obtain some sort of optimal or at least optimized predictions for traffic light control. So how does that work? Well, the basic idea is that we take the data and we take our reinforcement learning agent and we train it in a so-called digital twin. So that's a really important concept that we will also talk a little bit more about, like in the next slides. Digital twins in general are simulations of a real environment or so-called digital copies. And they're really useful because they allow you to train your reinforcement learning agents safely and efficiently. So the basic idea now is that these reinforcement learning agents can try out different types of control in these simulated environments. They obtain feedback in terms of what worked and what didn't work. And with that feedback, they can update and learn and optimize their predictions. Once we are happy with our predictions from our reinforcement learning agent, we feed it back into our real life use case and use our reinforcement learner to control the traffic lights. This approach has several advantages. So we can obtain optimized and learned control based on historical data, but also information like time of the day or current location. We can adjust our traffic light control to real-time traffic, what's actually going on today or in this hour. And we can also train our reinforcement learning agent in a simulated environment, such that we can train it in a safe and in an efficient way. And another advantage is that we, in this solution, only rely minimally, if at all, on human interventions. So we exclude a lot of bias or subjectivity in designing these systems. And research shows that it's really beneficial to do that. So research shows that moving from such a hard-coded conventional traffic light system into an actively controlled dynamic reinforcement learning system really has many benefits. For example, we can reduce the average waiting time of cars by up to 35%, and we can obtain an up to 40% reduction in traffic jam in general. Okay, so that's our first example. And the aim of this example was really to show you what it can help or what it can bring to the table to introduce reinforcement learning into your conventional problem. The thing that I haven't really told you much about is the actual steps that you need to take to build your reinforcement learner. And that's what we're going to look into in our second example in the context of energy management. So a second really nice example of a success story of reinforcement learning is trying to optimize energy consumption. And the particular use case that we want to focus on is in the context of reducing energy consumption of data centers. So in our digital age, it is clearly a very important issue to manage the energy consumption and the cost of running data centers. And these data centers will then be used to store your LinkedIn, posts or your TikTok videos and things like that. And a particularly important aspect of that is actually managing the cooling of these data centers. And by current estimates, we believe that about 1.5 to 2% of the global energy requirements goes into running these data centers in terms of energy demands. But even more importantly, by some estimates, it is believed that this will go up to 8% of global energy demand by 2030. And if we also include other types of information technology into that, then this will go up to 21%. And by the way, these are pre-ChatGPT estimates. So it is now likely to be even more than that. So as you can see, this is a very important problem, and it is a very important question of how we can improve that. And reinforcement learning has been shown to be a very powerful tool in addressing that issue. So before we go into the details of that, let's take a quick look at what is the general process of applying reinforcement learning to your business use case. And then we will look at how this is actually done in our energy use case. So in terms of key aspects of implementing reinforcement learning, we would usually start with defining the problem or defining the characteristics of our reinforcement learning problem. And that usually comes down to defining what is your state space, what is your action space, and what is the policy that can be learned or optimized. So those are the different pieces that you already saw in Brijesh's part in the beginning. The next part is then finding a suitable reward function for your problem. And that often also involves some sort of reward engineering. So we need to find a suitable reward function which balances reward. That means the thing it's trying to optimize, so like the positive aspects, whilst minimizing and controlling for different risks or costs in your problem. And finally, as I've already said, you should also create a simulated environment, which means you create a digital copy of the problem to train your reinforcement learning agent, which is generally called a digital twin. And many of you might actually have that available already. Okay, now let's take a look at what that looks like in our particular energy consumption problem. So what I'm going to talk about is an approach that was developed by Google DeepMind, which is a leading institution in developing real-world reinforcement learning solutions. And in this particular case, they developed a reinforcement learning system that controls data center cooling. And they did that based on 4 very straightforward steps. The first step was that they would introduce a cloud-based system which pulls a snapshot of the data center cooling by using thousands of physical sensors. And in doing so, we would essentially create a very high-dimensional state representation of our data center. Next step is to take our state and feed it into the agent, which in this particular case is a combination of different deep neural networks. And this would then make predictions about the future energy efficiency and temperature based on different proposed actions. So those will be building up the Q-value representation that you've seen in Brijesh's talk. And finally, based on these Q-values, our agent would select different actions based on a learned policy, which tries to achieve 2 things. First, it tries to minimize future energy consumption, while at the same time satisfy specific safety constraints. So it's really, really important that your data centers don't run low on energy and have fallouts. And to make sure that this is really achieved, they implemented a 4th step, which was actually taking these optimal actions and send them back to the data center where a local system would actually verify them and then really check that they don't violate any safety constraints. So using that system, the researchers could actually show that this is really efficient and they could really minimize the data center energy demand substantially. So for example, they could show that within a few months of training, they could really minimize or decrease the energy demand by about 30%. And this was proportional to the amount of training or simulation data that you have available. And that's a very general pattern. So the more training data or the more simulated data you have available to train your reinforcement learning agent, the better it would become. They could also show that once they've trained the reinforcement learning system and they would turn it on to manage the energy consumption, they could actually reduce the energy consumption by about 40% relative to a baseline. So together, that really shows that the application of reinforcement learning here to this really important problem was very successful. Okay, and now with that final part, we would like to move one level higher and actually reiterate the point that reinforcement learning is really widely applicable by following always the same algorithmic structure, as we will show. You can apply this framework to a lot of different use cases and apply it to, obtain optimized solutions with minimal subjective experience or interventions. So just as a very brief third example that is very different from the two that I've just talked about is the example of supply chain optimization. So reinforcement learning is also a very important tool in the context of logistics. And big companies like Amazon, for example, use reinforcement learning in order to optimize their supply chains, where the basic idea is that we train a reinforcement learning agent in order to find the best distribution of products to warehouses or the right amount of production of goods in factories. And the key point here is that this example is very different from optimizing energy, and it's very different from optimizing traffic lights systems. But essentially, we follow exactly the same logic. We just tailor it and adjust it to the specific example that we have here. So again, we define a state space, an action space, and a reward function. It's just the specific characteristics that will look different. So for example, in our state space here, we would now define states as what is the stock and the demand levels in our warehouses. Action space would reflect the possibility to move products between factories and warehouses or in between warehouses. And we will try to optimize a particular reward function in terms of maximizing the revenue from sold products whilst controlling and minimizing certain costs like production costs, storage costs, or transportation costs. And we will also try to avoid penalties in terms of the demand of clients might not be met. So again, the key point here is that we can solve a very different problem by following exactly the same characteristic and algorithmic logic. And just to show you the wide applicability of reinforcement learning, we would like to give you a few more examples about domains and different use cases where we follow the same logic and we can optimize solutions based on reinforcement. So reinforcement learning is also used a lot in the domain of automotive. For example, in the case of automated driving assistance system, where here states would reflect some information about the vehicle data, like sensor data or like speed or relative position to other objects, or road conditions and things like that. And based on these state representations, our reinforcement learner would learn to take actions like vehicle interventions in order to accelerate, brake, steer, or signal in order to optimize the passenger's safety and comfort. Reinforcement learning is also used a lot in the domain of finance, for example, in the case of automated stock trading, where states reflect certain market conditions like historical price data or moving averages, and the reinforcement learner can learn to take certain trading actions like buying, selling, holding in order to optimize or maximize the monetary return, whilst perhaps managing some risks. Reinforcement learning can also be used in the domain of healthcare, for example, in the case of hospital resource allocation, where we take a particular hospital state, like the current resources and the patient arrivals and so on, and we train a reinforcement learning agent in order to allocate resources in order to maximize or optimize for fast treatment and avoiding unused resources. Or as a final example, reinforcement learning is also used a lot in the domain of manufacturing, such as quality control, where the state reflects certain product characteristics like sensor readings and process parameters, and the reinforcement learner learns to take certain control actions like adjust the process, initiate rework or repair in order to detect and ideally avoid faulty products. And with that, we would like to finish this part with a general roadmap. So if you became interested in using reinforcement learning in your particular business use case, first of all, we are very happy to help. So if you're interested, feel free to get in touch and contact us. But we would also like to give you a general overview over the key steps of implementing reinforcement learning in your specific business use case. So as I've already said, you would usually start with creating a simulation environment, which means that we create a digital copy or a digital twin, which simulates the particular environment of your business problem and allows you to train your reinforcement learning agent safely and efficiently. You would then go into a model development phase where within your simulation environment, you can create and train different reinforcement learning algorithms and determine whichever is best suited in solving the problem. Once you've determined the best reinforcement learner, you can take it back into your industry use case and use your reinforcement learning control system and see how it performs. And then you would usually go into an iterative process of model deployment, assessment, and maintenance in order to determine that your reinforcement learner really works. And with that, I would like to hand over to Constantin, who will tell you about one of the most exciting recent developments, namely reinforcement learning from human feedback.
Yes, thank you, Brijesh and Philipp, for your part, and I will take over to talk about reinforcement learning from human feedback. Because, as many of you might have heard, one of the most interesting tools of our time, or which is ChatGPT, was, among others, was trained with reinforcement learning from human feedback. And because of that, I want to start with a little citation or definition of that topic. And I think ChatGPT might be a good expert to ask what this topic is all about. And ChatGPT says that reinforcement learning from human feedback is a machine learning approach that combines human expertise with reinforcement learning algorithms to improve the performance of an AI agent by providing evaluative feedback. Maybe this sounds a bit confusing, but actually it's quite simple. Reinforcement learning agents goes hand in hand with humans, and they try to figure out what's the best solution in every situation they observe. So how does this look like, for example, in training a reinforcement learning agent with human feedback, in this case, ChatGPT? You can imagine that ChatGPT produces an answer set in the training process, like in this case, 4 outputs. And then there is a reinforcement learning agent who is in the training process decided to choose output C, as it thinks maybe this is the best answer in the current situation. And then, as we have learned, there's always a reward function, which is essential for the decision of the agent. And in the training process of the reward model, we check whether the solution that the reinforcement learning agent chose, in this case C, is the best answer in the solution in the current situation we observe. And therefore, we have our reward model that, for example, ranks the outputs, all 4 different outputs. So it says that D is slightly better than A and C is better than D, and the optimal answer might be B. But as in some cases, our human knowledge is above the level of artificial intelligence, we want to include it in the training process of machine learning algorithms or artificial intelligent solutions. And thus, we have on the other side humans who also rank the outputs of the reinforcement learning agent. And in this case, we say, okay, A is slightly better than C and B is better than A. Even if the reward model says that B is the optimal solution, the human overvotes the reward model and says, no, D is the best solution. And this difference between those 2 rankings can then be used to optimize the reward model so that the reinforcement learning agent learns to choose the best answer in the next iteration. In this case, it would be D. So this is a part of how ChatGPT was trained. But let us have a look at another example, the traffic light example, which Philipp was talking about earlier. So as you might remember, we have our optimization problem of traffic lights. And in this situation, we have here a scene, and the reinforcement learning agent asked the reward model for feedback, and we want to train the reward model in this case also with human feedback. And you can think of it like this process is of course starting with the reward function. So when we train the reward model, we always have a reward function. In this case, we might want to reduce congestions, we want to reduce traveling time, or maximize the traffic flow efficiency. And for example, at this step, the reward function outputs action to switch to yellow for a specific traffic light. But we know that we have some experts or a group of experts that has more knowledge about some situations, and we want to include this knowledge of our human expert group to train the reward model. And like in the previous example, we can include human feedback by providing demonstration of experts controlling the traffic light system, or they rank different scenarios, etc. And it's always the same. You have the difference between the action from the reward model and the action that the human feedback provides. And then we use this for update the reward signal so that the reinforcement learning agent then can be trained with a reward model that is a combination of the trial and error and the human signals that were included. So this was a very short introduction to reinforcement learning from human feedback. But I think in some cases it is very useful to include in the reinforcement learning training process. And with that, I want to come to a conclusion of our today's webinar. And at first, let us have a look at this, quite overwhelming slide with all the industries. But what I want to highlight here is, what Philipp already said, that it doesn't depend on the industry that you are in, whether you can model your problem as a reinforcement learning solution. So what we want to encourage you is, whenever you have a decision-making problem where you want to choose the best action at time, but you don't know how to model the actions, and spaces, action space and reward function, come to us. We will have a look at it, whether it's feasible, and don't think that there are any industries where reinforcement learning cannot be applied. And then just to remember the different benefits of reinforcement learning. And I think one of the most popular benefit is that we don't need labeled data. And if you're in the field of machine learning, you know that labeled data is usually time-consuming or cost-extensive or both. And as reinforcement learning agents were learned by trial and error to find the optimal policy, which is the second benefit, we don't need those labeled data. And then, of course, we have the advantage that because of the exploration trade-off, we can find solutions that might not have the best outcome in the current situation, but will lead to a higher reward in the future. So we will also explore different scenarios that have a long-term goal or lead to a long-term goal. And then I want to come to adaptability, because what's always in machine learning a point is that you want to understand what's going on, either in the inference process or in the training process. And in this case, it's quite easy to understand, because the learning process is very similar to the way we humans learn, like Brijesh told in the beginning. And at this point, I want to highlight the article from Philipp, who was published, I think, last week, where he discusses the part of neuroscience in reinforcement learning systems. And then the last advantage I want to highlight is that it is up to a certain amount bias resistant. We heard that because of the trial and error, it explores all possible solutions, and thus it is not influenced by any subjective data. The only bias that influences the reinforcement learning agent is the reward function, but this can be engineered very well, and so it's more bias resistant than most of the other machine learning tasks. So here, a quick overview of the roadmap. So like Philipp said, we have the simulation environment. When we have modeled a digital twin, we can train the reinforcement learning agent in the safe environment before we will leave it out to the real world system integration, where we will apply it in your real world scenarios. And then, of course, this model needs to be maintained and deployed over time when it was retrained, etc. So, as to close our webinar, let's have a look at this cycle, and we want to start at the upper left. How we can use reinforcement learning in business applications. Of course, it is always useful, like I mentioned, if you have a sequential decision problem, wherever you are in which industry you are in, you can think of using reinforcement learning to solve those sequential decision problems. And then based on trial and error, we don't need any labeled data. We can learn or train a reinforcement learning algorithm by simply defining space, the state action space and the reward function. And this can be applied to many different tasks that can be solved. And then when we have those tasks defined, when we have the state action space and reward function defined, and we can simulate our virtual environment that we want to train the algorithm in. And when this is finished and we leave it out to the real world, we can also think about including humans in the loop. So when we have some expert that have even more knowledge than the reinforcement learning agent gains by trial and error, we can also think about reinforcement learning from human feedback to get even more powerful reinforcement learning systems. And with this, I want to say thank you for your attention. I want to ask my colleagues back on stage so that we can have a look at your questions, and feel free to type in your questions and we will do our best to answer it. So we're singing.
Yeah.
It's not sharing anymore?
No.
All right.
I think we had one question.
Yes, I think I did see one question at least on the actions and action space. Can we maybe open that again?
This one.
I think there was one before that.
I thought that.
I mean, just in general, so that if I remember the question correctly, this one?
Yeah, this one.
Exactly. So is the list of actions that an agent can take limited? So that's generally a very, very interesting question, which leads to like the huge topic of like applying reinforcement learning to like real world scenarios. And basically, if you take the most influential book on reinforcement learning, which is called Introduction to Reinforcement Learning by Richard Sutton and Andrew Bartu, they would actually have like these two parts. First of all, the first part is on tabular reinforcement learning, which basically means we go through the entire theory of reinforcement learning, but mostly with like toy problems where we can basically write down 5 different states that the agent can be in, and it takes 2 actions or it navigates around or something like that. And then the second part of the book is actually applying it to like realistic problems, like approximation problems, where the state space and the action space becomes realistic, which means much larger. So we need to specify the action space in advance, but if you want to cast your specific business problem as reinforcement learning, you would have to deal with a usually like a huge state space, a huge action space, which can either be discrete or continuous, as Alex already pointed out, and very often has to be approximated by, for example, neural networks. And that comes with its own challenges. I believe Brijesh just wrote a blog about that in terms of the deadly triad. That's also interesting.
Yeah, so it will be out next week, but the blog is basically about that we are using a big neural network. And when we use neural networks, if there is some change in prediction of one output, and we try to update those or accommodate those changes, then it will also change the outputs of other situations where we actually did not want to update the changes. So yeah, it will be an interesting read when it comes out next week. And just to continue, we can also link the next question with it for discrete and continuous actions. So it is about can we use reinforcement learning in marketing? So let's say if we have multiple marketing campaigns, or let's say website design, then this is like a discrete action. We tell an agent for every new user, you can select either one of the 2 website designs. And over a period of time, it will learn to provide that website to the user, which has higher, let's say, readability of a blog, or we get higher marketing requests. And in case of, let's say, autonomous driving, where we have various different acceleration and braking levels, there you need a continuous action space. So you should be able to accelerate from 0 to, I don't know, around 5-7 meters per second square or something like that. Yeah, so it basically depends on the use case and how we want to model the problem.
Exactly. So as we try to point out, it always comes down to really specifying what is your state, what is your action, what is your reward function. There are researchers who say every problem can be cast as reinforcement learning problem. You just have to get this right. And sometimes you have to be a little more creative. Like in the case of marketing, you need to think, what is a reward function? Well, I guess a reward function will reflect something like, there will be more readers or people will maintain with a particular article or with a product. And actions would be, as we just said, suggesting certain website, things like that, but it's certainly applicable and possible as a reinforcement learning problem.
So let's have a look if there are any other questions. Oh, there's one. Oh, and it was, thank you. Yeah, you were very welcome.
Thank you.
That's the next one. So, do you have more book recommendations for reinforcement learning? Maybe I can start, even if it's not a book recommendation, but what I think is a really good source to diving into this topic are the Stanford videos. So Stanford provide videos here on YouTube. They're free accessible, and they will give you a very good overview of the different the different parts we discussed here on high level, and they provide you also with the deep dive of it. So maybe this is a good starting point.
Yeah. And we also did the Hugging Face reinforcement learning course. So this course actually helps you dive directly into the practical applications and how you model the problems. This is an important resource. We also have some reinforcement learning environments on OpenAI website or OpenAI Gym website, where they also have like good documentation on how to model a problem as a reinforcement learning problem. And yeah, we'll be sharing a Q&A that contains a lot more resources on how to get started with reinforcement learning. So this could be quite helpful.
Yeah. So because Alex did a very quick overview of some different learning starting points, and we will collect it in a Q&A document and provide it to all of you. So it seems there are the questions. Isn't this one not? Let's go into this one. No. Here it is. So let's start maybe. Is reinforcement learning used a lot in modern AI application? If so, how? So I think.
Well, I can start. So I mean, I guess our general point here would be yes. That was the whole point. So I think as long as your question and your problem has a certain degree of complexity, where you try to optimize something, possibly have a sequential problem, not necessarily, but ideally, where you need to make decisions or actions, then reinforcement learning is really, really useful. And it turns out that most of the state-of-the-art AI applications that are currently in the news and people get excited about have a reinforcement learning component in it, because it's just such an efficient optimization tool. And so even things, as we've heard, like ChatGPT, which at a first glance don't seem like a reinforcement learning problem, have a very important reinforcement learning component by learning to actually produce good dialogue. So that brings us back to this point of what can be cast as a reinforcement learning problem. Well, if you get the reward function right, basically everything. So in most of the sophisticated, new algorithms beating the best human players in chess or in Go or finding new protein folds, that would rely on reinforcement learning. So my answer would be yes. I don't know if you.
Yeah. I mean, you wrote an article on different use cases, so there are plenty of them.
All right. Maybe I'll take even it's not the sequential next question, but I'll take it over because you mentioned ChatGPT. Because here's the question: what advantages over reinforcement learning from human feedback over traditional reinforcement learning? there are some advantages, and I think one of the main advantage is sometimes you don't can engineer a very detailed reward function, and then you want to have human feedback in the loop so that it guides the reward function towards the best towards the best outcome. And the second part is sometimes you also want to exclude some behavior of the reinforcement learning agent model. For example, this is one case why OpenAI use not only OpenAI but most of the other big players also use reinforcement learning from human feedback in the training process, because you want to that the reinforcement learning agent or the large language model do not output some harmful behavior or some very toxic behavior, etc. So as we have learned, the agent just out of trial and error, and you want to make sure that it doesn't choose any of those toxic, harmful behavior or biases that are included in the data. Yeah. So then I come to read the next question. How can I avoid reward hacking?
So this is a quite interesting topic. So honestly, we have to think about what kind of rewards are we giving to the agent. So generally they are like very complex rewards, so that we restrict the so there are some positive rewards and negative rewards. Negative rewards are the ones where we restrict an agent from doing particular things. So I'll give you a small example where an agent actually tried to hack the reward function. So I had this autonomous emergency braking system, and what the agent figured out was it takes it so every 1 second I give it +1 reward. And if it hits the vehicle in front with enough velocity, then it will rebound on the road in front of it, so that it needs another 11 seconds to go and hit the vehicle in front again. So every time it does that cycle, it gets +11 points for traveling to the vehicle in front and -10 points for crashing with the vehicle. But in general, it was getting +1 point for every time it repeated the cycle. So it ended up repeating this cycle long enough to get more and more reward. So here the main thing was that when it crashes into the vehicle in front, we provide a larger negative reward. So we have to properly analyze the reward structure, the reward function, and then see how could it affect the behavior of the agent, so to say.
All right, and then so far the last question, but you have 5 minutes left to get your question answered directly. But of course, maybe there's one other hint. If you have any questions after the webinar or when you have discussed the input with your colleagues, feel free to contact us on LinkedIn or via email. We are very happy to help you out. So the last question until now is, how do I evaluate the potential of reinforcement learning for my business?
I think Brijesh might also be to say something.
So honestly, there are 3 steps in this process. So first of all, we would need to develop a prototype for a business use case. And based on this prototype, we need to see the cost and resource benefit usage analysis. If it is good enough and there are enough benefits for the company, then I think it makes sense to move to the next step where, like Philipp and Constantin said, we have to develop a model, we have to deploy it, and then we enter into this iterative cycle of generating or making the model more adaptive, teaching it new things, and it improves over a period of time.
So there's another question that came in right now. So it was asked if a human in the loop in reinforcement learning is a bit like adding labeling of data to reinforcement learning, and therefore removing the advantages of not having to label data. Yeah, it is quite like this. It's like a trade-off, because you don't have to label all the data, but you use labeled data from human to influence the reward function. So you try to get the most out of both approaches.
Yeah, and I think you can also get into concepts like likability of something. So, for example, like the human likability of a particular conversation with ChatGPT, which is very hard to define in terms of the labeling. So you can really get into, you still have that. So reinforcement learning is very strong when you don't know exactly what labels there are. You just don't want to label everything, but you might still be able to classify something as good or bad, but you don't quite know how. And that's kind of like a nice compromise, as Connie just said. In terms of introducing some useful labels, but not having to know what they really are or what they really mean. So I think it's quite nice, but it's a very nice question.
And this would also help us reduce the training time. So the agent doesn't need a lot of time to analyze that this was a wrong answer.
Yeah. All right. So then we're 2 minutes ahead of time, but it seems that there are no questions. Then thank you. As we mentioned, if you have anything, later this week or next week, feel free to ask, contact us. And have a great rest of the week, I would say.
Thanks very much. Yes.
Thank you
for tuning in.